Hello, I'm Ivan Fedyanin. I'm a software architect and a PhD. In this series of videos, I'm covering different topics of distributed systems, and my goal is to make difficult topics to be understandable and clear for you. So today's topic is client-centric consistency models, and let's start with it. Content of this lesson is presented on the screen now. You can see it, and also you can open the description and click on the navigatable links just to get to the exact time what you are interested in to, for example, check some specific topic. But I recommend you to start full video because one topic depends on another sometimes, and it would be much better to view it all from the beginning to the end. Before we start looking at specific session guarantees, first let's try to see big picture, because if we understand big picture, we understand how small bricks, how small parts fit together. And I believe that understanding big picture is very important. So why do we need session guarantees at all? First, we know that we have strongly consistent systems and weakly consistent systems. Strongly consistent systems like linear readability, sequential consistency, those models, they provide very intuitive behavior and lack of anomalies because they are very strict, and little amount of execution is possible within those models. But the trade-off is that systems which support strong consistency models, they have problems with availability, scalability. They are not performant, and they are not simple. So yeah, it's simple to use them, but they itself internally they are quite complex. And also such system doesn't work well in mobile computing environment, because it's natural that mobile device can go offline at any moment. It can lose network, and it can lose power, and so on. And if a device goes offline, then we have a choice. Either we have to stop accepting all writes to the system, because otherwise if we write something while a part of the system is offline, it means that there will be inconsistency, or we will have to sacrifice consistency. And with strong consistency systems, it's not really possible. So, and on the other hand, we have weakly consistent systems. Those systems, they have a lot of benefits. They are available, they are scalable, performant, simple. They fit well with mobile computing. But we have to pay for this with another problems like anomalies and lack of reasonable behavior. Because usually weakly consistent systems, such as eventually consistent systems, they contain a lot of different replicas, and basically there are not much guarantees to what the data in those replicas. So it's possible that in one replica we have one piece of data, on another replica another piece of data, and they, in general, they could be conflicting with each other. And if we have to create an application to work with such a weakly consistent data store, it could be a nightmare for a developer to work around over all of those anomalies and corner cases, and there are a lot of them. And if some corner case is missed, then it will be exposed to the user, and it could make the user to be frustrated. Also, it can be noticed that usually all problems with weakly consistent system, they come from the fact that client could connect to any replica. And for example, if client could always stick to one replica, then most problems of weakly consistent systems would be resolved. But in general, we don't want a client to restrict to only one replica. And here are how session guarantees are coming. Basically, session guarantees And client consistency models, it's the same thing, but two different names for it introduced in different literature. And session guarantees, it's some constraints that are applied on top of the weakly consistent systems and which make their behavior reasonable. And they significantly reduce amount of anomalies. So we have a weakly consistent system. On top of it, we apply session guarantees. And as a result, we have a system with all benefits of a weakly consistent system and reasonable behavior. And that's a big win. So initially, 4 session guarantees were introduced: read your writes, monotonic reads, monotonic writes, and write follows read. And also later, the same authors, by the way, it was Terry and the company, introduced another guarantee, which is called consistent prefix read. And also, I'd like to mention that achieving those session guarantees, it's relatively easy and cheap. So it's much cheaper to use a weakly consistent system with session guarantees than to use strongly consistent system. Okay, that was the big picture, and now let's look at each of the session guarantees one by one. We start from read your writes. It's very simple, and it basically says that if a user in scope of a session makes write and then makes read, then it's guaranteed that this user should see his own write during the read. So let's look at the example. There is a client and there is a data store with 3 replicas. And there is a session, a red circle, which depicts a session. And in scope of the session, client makes 2 operations. At the moment T1, it makes the write, W, and then at the moment of T2, it reads it. And we see that during the read, it lands on different replica, on replica number 2. And but still, it can read this write W, which he just wrote before. And this is the nature of guarantee read your writes. And also pay attention to the read R3 made at time T3. It's made out of the session by the same client, and now it does not get anything from the database because we don't have any guarantees on operations made out of the session. So it could return write W, but it doesn't have to. Okay, now let's see more complex example when the guarantee read your writes holds. Here we have a system with 2 replicas. We have Alice and Bob, and Alice writes x1 to replica 1, and then it's being propagated to replica 2. And after that, Bob writes x2 to replica 2. And now Alice wants to make the read, and she lands on replica 2 and gets x2. So the point here which makes the system satisfy read your writes guarantee, that Alice, by the time of read, of her second read, she lands on a replica which already has her write, which was done previously in scope of the same session. Now let's see what would happen if this guarantee does not hold. It's a very similar situation, but the propagation of write from replica 1 to replica 2 fails for some reason. And despite the fact that Alice receives the same version of X, which is X2 on her read, the guarantee is violated because by the time Alice receives it, there is no X1, which was her previous write on the same replica. Now let's see kind of real-world example of reading your writes. We have here authentication system which allows to authenticate with password, and it allows user to set her password. This system has 2 replicas at the moment of T1, and each replica contains first version of Alice's password, like previous version. And Alice now wants to update her password in the system, and she issues an update and sets password to v2. And this happens on replica 1. And then at the moment T2, Alice wants to verify her password just to log in. And now she lands on replica 2, and this replica 2 doesn't have this password yet because it wasn't yet propagated. And in that case, Alice would receive like failure and message that her password was incorrect, despite the fact she just changed it. It happened because system violated read-your-writes guarantee. And if the system satisfied read-your-write guarantee, then such situation could not have happened. So it's an example of situations when we need read-your-writes guarantee. Now let's see monotonic reads guarantee, and first let's see its definition. Definition basically says that if client makes several reads in scope of one session, then those reads must return non-decreasing set of writes. It means basically if user has already seen some write in scope of her read, then on the second read in scope of the same session, it's guaranteed that the user will see previous write as well. And here it's illustrated. We have a red circle which depicts a session and two reads, R1 and R2. And by the moment of R1, which landed on replica 1, it contained two writes, W1 and W2. And on read R2, the read now lands on replica 2, and we see that W1 and W2 are still there. So it means that set of writes which is seen by client is non-decreasing. And also we have W3, which might just come later. So a guarantee holds here. And also pay attention to the read made out of the session. It's read R3. It lands on third replica, and it's not guaranteed to see non-decreasing set of writes because it's done out of the session. So it's the concept of the session is important here. An example when the guarantee is violated. We have three replicas here, Alice and Bob. And Alice makes the write of value A to replica 1, and it's being propagated to replicas 2 and 3. But the propagation to replica 3, it's kind of delayed a lot. And during this time when it's delayed, Bob makes two reads. And those two reads are made by Bob in scope of one session. And here, first read of Bob lands on replica 2 and gets A as a result. And his second read gets on replica 3, which yet does not have write A, because it was not yet propagated. And Bob gets null as a result. This is a violation of monotonic reads because Bob sees a decreasing set of writes. Basically, Bob sees into the past because now he already knows that A is in the system, and on his second read, A is not in the system, and no one removed it. It means that Bob is looking in the replica which is in the past. So with monotonic reads, this could not have happened. Here we have emails management system, and basically the only capability of this system is to receive emails through the balancer and balance it to replica 1 and replica 2, and then there is some kind of replication happens between replicas. For the purpose of the example, we don't really care which type of replication here is happening. And this system provides Alice with the ability to read emails, and Alice could read emails from two replicas. Assume that we have following picture as shown here. Replica 1 has emails from 1 to 3, and replica 2 has emails 4 and 5. And first Alice read was on replica 1, and she has seen previous first 3 emails. And when she switched to replica 2, for some reason, for example, she moved to another location or just balancer balanced her request to a different session, on that replica there are only emails 4 and 5. And if there is no monotonic reads, then for Alice it would seem like previous 3 emails have gone, and it would be very confusing. On the other hand, if we had monotonic reads, then it would be guaranteed that on her second read, Alice would read at least first 3 emails and possibly other emails like 4 and 5. Now let's see some ways how this monotonic reads guarantee could be achieved. The first option how we could achieve monotonic reads guarantee here is to make synchronous replication. In that case, replica, before making those writes available for reads, it has to ensure that they are replicated to another replica. In that case, emails 1, 2, and 3 would be available for reading from replica 1 only after they are propagated to replica 2. It means that if Alice read them on replica 1, she would surely be able to read them on replica 2 as well. If we don't want to introduce synchronous replication, another option is just to make Alice to always connect to replica 1 or to replica 2, it doesn't matter. If Alice always connects to the same replica, then the amount of data on that replica would be always non-decreasing. And the third option, which we could use here, it could involve Alice, a client side. When Alice reads data from replica, it could remember some kind of version of the replica. And when Alice connects to another replica, it could provide additional parameter, this version of the data which she read on previous replica. And then, for example, replica 2 could detect that Alice has already seen some US data which are not yet available on replica 2. At this moment, replica 2 could pause with the response to Alice and wait until the replication happens. Or, for example, it could proactively request this data from replica 1 and return them to Alice. So it's just 3 simple examples on how we could achieve monotonic reads. Next, let's review write follows read guarantee. The main idea, if client has read some data and then made the write, then whoever sees the write of the client would also see all writes which led to result of the previous read of the client. It sounds a bit complex, so let's see on the illustration. And here we have a red circle which depicts a session. In scope of that session, Alice makes first read R1 and at the moment of T1, and during that read, W1 was already available at replica 1, and it returned to Alice. And then Alice made write W2. It's depicted here with dotted line because it was done after she already seen W1. And now the fact that Alice has seen W1 when making W2, now it binds those 2 writes together, and it basically says that whoever sees W2, it must have as well W1, and they should be ordered in the same order. And note that the effects of this write follows read, they are applied outside of the session as well. Because Bob here, it's separate session. It might not have a session at all, but anyway, he might make the read, and it's guaranteed that if he sees W2, then W1 as well should be in the same replica. But at the same time, there is no such restriction for W1. It's perfectly possible that some replica has W1 but doesn't yet have W2. Now the examples when this guarantee holds. Alice makes the write x1 to replica 2, and then it's propagated to replicas 1 and 3, and then Bob makes the read. It reads from replica 3 first and gets x1, and then Bob makes the read. First it reads from replica 3 and gets x1, and then it writes to replica 1 the value x2, The idea here is that when Bob writes x2 on replica 1, this replica already has a write x1, which Bob has seen during his read. And it's assumed here that those read and write made by Bob, they are done within one session. If we made a small change and just consider the case when write x1 didn't propagate to replica 1, then Bob also could make the read, it could see x1, and then it could write x2 to replica 1. But this replica now, it doesn't have x1, but write follows read says that if Bob has seen x1, then when he makes the write, it must arrive on the replica which must have this x1, and it doesn't. It means that the guarantee is violated here. Let's see kind of real-world example which uses write follows read guarantee. Assume that we have a system of management of events. By events I mean real-world events which have a date and a place and an ID. Before we start considering it, let's assume that there are two writes made into that system into table events. Firstly, we insert into events record with ID 1, January 1st, and place London. And then someone updates the table of events by ID and sets place equals Lisbon. Now let's see what happens. Alice, at the time of T3, Alice makes the select from events by ID, and she gets those data shown here. And we see that those data, they reflect both writes. First insert and that later update, because we have date January 1st and the place Lisbon. It means basically that Alice has seen two of those writes, and then Alice wants to update an event and change the date to January 2nd. The guarantee write follows read guarantees us that in the end we will have this record. It will happen on January 2nd and in Lisbon. Those outcomes in the red, they are impossible, because write follows read guarantees us that whatever replica which was hit with this update, this replica would have everything which was read by Alice, and in our case it's those two writes. It was quite easy so far, so now let's try to look a bit deeper. It could be noticed that write follows read guarantee, it consists of two independent constraints. First, let's assume that we have read R1, and in scope of this read R1, client read the results of write W1, and then made write W2. And then the constraints are following. First constraint is on the order in which W1 and W2 are propagated across replicas. This can be easily seen on this picture. So we see that by the time W2 is not yet arrived, W1 is already in the replica. So this is propagation order, how those two writes W1 and W2 propagated between replicas. And what is important here, that W1 got to this replica first. And the second constraint is write order. It's depicted with the green rectangle, and it means the global order of writes, which all replicas will eventually reflect. It's not order in which they arrived, but it's an order which are ordered by some attribute, for example, which could uniquely establish order between two events. Write follows read, it requires two of those guarantees at the same time. But we could look and explore some partial constraints which involve only one constraint. So first let's see simplified version of write follows read, where only write order constraint holds and we don't care about propagation order. In that case, the situation could be following. Assume that two writes W1 and W2 happened in some replica, and then they are propagated, and this is the replica which receives those propagated writes. And here we see that they arrive out of order. So the propagation order is wrong. First we have W2 and only then W1. But here in that case we care only about write order constraint. So after a replica receives both writes, they are ordered properly. For example, they could be ordered by some attribute inside of those writes, some metadata. For example, this metadata could contain timestamp when this order was executed. In the case of conflicts, there could be some rule how to order them uniquely. And here it's guaranteed that the write order will be correct despite possible incorrect propagation order. And let's see how this simplified partial write follows read constraint with only write order constraint could help us. Here we have exactly the same system as before for managing events, and assume that current state of the system is that one. When Alice makes the select, it gets date January 1st and place Lisbon, and then she wants to make the same update as in previous case, but now she can't make partial incremental update by ID because we don't have constraint on propagation order, and because of this Alice has to make full update or insert events into this table just in case replica where she lands on doesn't yet have the right version of the data. It might not have the right version of the data because we don't have propagation constraint. So Alice has to make full update or insert and provide the target version of data she wants to have. And because we have write order constraint, it's guaranteed that when Alice makes this update, even if replica did not have this data and they arrived after the update, when all of the events arrive to the replica, they will be ordered properly, and those first two inserts and updates, they could be simply ignored, and the last update or insert will take place because we have write order constraint. Now let's look at the opposite situation when we have only propagation constraint, but we don't have write order constraint. So now it's important for us that the replica receives first W1 and then W2, but inside of that replica, their global order, it might be different. It doesn't matter for us. And here it's an example how such a propagation constraint could be used. Now we have inserted into events event which will happen in London on January 1st. Alice at the moment T2, she read that event and it's returned to her. And now propagation constraint says that this insert must arrive to replicas before another insert which Alice made after that. And here Alice wants to attend this event and insert a record into attendees table which references ID of the Alice, name of the Alice, and the ID of the event she wants to attend. Now, because propagation order is guaranteed, it's guaranteed that any replica which has this record in the attendees table, it will also have event in events table. Because of this, the system will work correctly. And the write order does not matter here for us because those two writes, they are not conflicting. So we are only curious about their order of propagation. By now we have reviewed write follows read constraint, and also we split it into two parts and has seen how they are different and what different constraints there are. It's worth noting that this system also could be done with full write follows read constraint. So why to bother and why to have only partial constraint? So there are two reasons. First reason is that the less constraints we have, usually the better for the performance. So if we can, instead of requiring two constraints, could require only one constraint, and it does not impact our system, then the performance will improve and it's beneficial for us. And second reason, it's just very useful to see two different orders here, because they will be used later in more sophisticated consistency models. Now let's go to monotonic writes. Monotonic writes basically says that if two writes are made within one session, then whoever sees the second write also will have to see the first write. So we have an Alice here. She makes two writes W1 and W2 in scope of one session, and then out of this session, because for reading in this case the concept of session doesn't matter, Bob makes two reads, R2 and R3, and during R2 Bob sees both of those writes, and basically it's guaranteed that if he sees write W2, he must also see write W1. What happens here? And this here, when Bob makes read R3, he sees only W1. So it does not violate monotonic writes, because it says nothing about W1. It says only that if a replica has W2, it must also have W1. An example of when this guarantee holds is simple. So Alice makes two writes, X1 and X3. It's propagated to replica 2 when she makes it, and in meanwhile Bob also made the write to replica 2. And monotonic writes guarantee holds because by the time Alice makes write X3, this replica already has write X1. And if this propagation did not happen, then monotonic writes would be violated, because by the time Alice makes write X3, this replica does not have previous write which Alice made in scope of the same session. So it's violated despite end result would be the same. So in the end, all replicas will reflect X3 in this example. Let's see application which could happen in real world, which could require monotonic writes. We have some storage where artifacts are stored. We have application and a library. And application of version 1 can work only with library version 1. And it can't work with library version 2. So if we want to update application and the library, first we have to update application to the next version, and then we have to update library. In that case, monotonic writes would be needed because we want to ensure that if we updated application first, then it's got distributed to all replicas before library version 2 distributed to all replicas. In that case, the system will remain functioning at any moment of time. In this example, Alice does the writes to only replica 1. And in that case, it's trivial. It happens automatically that those writes propagated in the same order Alice made them. Let's look at the same situation, but in more complex case, when Alice write could land on any replica, on replica 1 or in replica 2. So first, Alice connects to replica 1 and updates application to second version. Now Alice wants to update library, but it lands on another replica. So in this case, replica 2, it must comply with the monotonic writes. It must detect that those two writes were in scope of one session, and library write has to wait until application write happens and it's arrived to replica 2. So it waits and holds with the request of update of the library, and now when application is updated on replica 2, it can accept and process update of the library as well. So in such system, monotonic writes are required so that it could function properly. Now let's go to consistent prefix read. And the general idea that whenever we see an operation, we'll also see all operations that proceeded in arbitration order. Arbitration order is the order the operations were written to the system, or in case they are concurrent, some rule is established on how they are ordered. So here we have an example of system which contains 5 replicas, And we have ordered set of writes. This is the order of writes which were happening in the system. So first we set x to 1, then updated it to 2, then updated to y, and so on. And those are the replicas, and above those replicas we show what data they are allowed to have, having consistent prefix read guarantee enabled for this system. It's called consistent prefix because, as we see, each set of write it's a prefix of this global set of write. So basically it means that whenever we read data from the replicas, we read the state of the system which really existed at some point in the past. So the idea is that, for example, if we read from replica 3, then it has first 3 writes, which are basically those first 3 writes. Now let's compare consistent prefix read to see how it is different from monotonic reads, which we reviewed previously. Assume that here we have a system which satisfies monotonic reads. It's basically exactly the same picture on the previous slide from the data point of view. And now let's introduce client who makes 2 reads. Read 1 lands on replica 5 and reads all this amount of writes. And then client makes read number 2. And this read lands on replica 1. And client sees only 1 read. So the rule that client must see non-decreasing set of writes, it's violated. So by this illustration, we see that system that provides consistent prefix read guarantee, it does not have to provide monotonic reads, and monotonic reads still could be easily violated. Let's look in another case when we have system that provides monotonic reads. Let's see whether it has to be consistent prefix read as well. Assume that we have 2 writes happened in that specific order. First we wrote x1 and then we wrote y equals 1. And then we have a system which supports monotonic reads. Our first read made by client landed on replica 2 and has seen 1 write. And the second read landed on replica 3 and this read returned 2 writes. So we have non-decreasing set of writes because here we had 1 write and here we have 2 writes including previous. So from monotonic reads perspective, it's perfectly satisfied. But we see that consistent prefix is not satisfied because during read R1, client has seen state of the system which did not exist because system with y equals 1 did not exist without x because x update of x was the first one. So from this we can arrive to conclusion that consistent prefix read and monotonic reads, they are completely orthogonal and the existence of one does not say anything about other. Now let's compare monotonic writes and consistent prefix reads. Firstly, from the definition, it can be easily seen that if system supports consistent prefix read guarantee, it automatically supports monotonic writes. Because monotonic writes, they are scoped only to one session, and consistent prefix reads, it applies to the system in general, but the opposite does not hold. If the system supports monotonic writes, it does not mean that it will be consistent prefix read enabled. Let's see an example. We have Alice, which makes 2 writes, W1 and W3, in the replica 1, and between them Bob writes W2. From the requirements to monotonic writes, now write W1 and W3, they are bounded together because they are made in the scope of the same session. And for example, on replica 2, we have only those 2 writes, W1 and W3. And it's perfect from point of view monotonic writes, but consistent prefix is violated here because W2 is not there. And it's not a real state of the system which existed at some point in time in the past, because first we had W1, then W1 together with W2, and only then W1, W2, and W3. So this is not existent state, and consistent prefix reads are not working here. Next, let's see read-your-writes and consistent prefix reads. So let's assume that we have a system which supports consistent prefix reads. It means that the data could be distributed across replicas in the way shown in the picture. So each replica has some consistent prefix of all set of writes. And assume that before time t0, Alice made all of those writes by herself. And then she wants to make the read. And she could land to replica 1, for example. And this replica 1, it has only one write. But Alice already made 5 writes. It means that Alice does not see all her writes. It means that read-your-writes is violated in consistent prefix reads. And let's check the other side of the situation. Let's assume that read-your-writes is satisfied. And what will happen with consistent prefix read? We have Alice here and Bob. Alice makes write W1, then at time t2, Bob writes W2 to the same replica. Then, in scope of the same session, Bob makes read, and it reads only W2 because from the guarantee read-your-writes, Bob made only one write, W2, and Bob reads this write. So it means the system supports read-your-write guarantee, but consistent prefix read is not supported here because again we have W2 without W1. So we've just shown that they are different. Let's compare write follows read with consistent prefix reads. First, consistent prefix reads guarantee implies write follows read because it's more general. It can be seen from the definition. And here let's illustrate and consider opposite case when we have write follows read guarantee, but we don't have consistent prefix reads. Here Alice in scope of the session first makes read R1 and she gets W1 as a result of this read, and then she makes write W2. Now those two writes, they are bound with write follows read guarantee. And then Bob makes write W3. Then if reads and gets only W3 from second replica. So from write follows read, it's perfect because there's nothing about W3 which is guaranteed because it's not related to W1 and W3 because they are done in different sessions. So write follows read is not violated here, but consistent prefix read is violated because system never had a state when only W3 is available, but W1 and W2 are not available. So by this time, we have already reviewed 5 session guarantees, and they have seen the differences between them, and they're actually different. And sometimes we might require several session guarantees for our specific case. Let's check a relationship of client-centric consistency models or session guarantees with causal and FIFO consistency. First, if we have put together monotonic reads, monotonic writes, and read-your-writes, then such system will be FIFO consistent. But the opposite does not hold, and we will show it later. But if we combine 4 session guarantees, monotonic reads, monotonic writes, read-your-writes, and write follows read, then we have causal consistency. And the opposite works as well. If we have causally consistent system, then monotonic writes, monotonic reads, read-your-writes, and the write follows read also will be held in such system. Let's look deeper why FIFO consistency does not imply session guarantees or client-centric consistency models. Firstly, I'd like to highlight that I have a separate video about consistency models, and in that video I show how FIFO consistency system works in the detail. Now I'll just briefly tell that in FIFO consistency, writes and reads are served from local storages of the servers, and after the write there is asynchronous notification about this write sent to all other servers. Let's assume that Alice made 2 writes, W1 at time t1 to server B and W2 at time t2 on server C. And we know that in FIFO consistent systems, notification about those two writes will be sent to all other servers, and eventually they will apply those changes. Right after Alice made those two writes, she might read, for example, from server B. And on server B, she will get back only W1 because the other write is not yet propagated there. So she has seen W1 and then she switches to server C. And on server C, W1 is not yet propagated and she reads only W2. It means that Alice sees decreasing set of writes because previously she read W1 and her second read she did not read W1. It means that monotonic reads guarantee is violated. Next, let's see monotonic writes. Monotonic writes basically says that if Alice made W2 after W1, then if she sees W2, she must also see W1. And it's also not true because if Alice makes the read from server C, where W1 is already stored, W1 might not yet been propagated, and she will not see W1, despite the fact she did it before W2. And read your writes also does not hold. For example, Alice made those two writes, and immediately after that she made read on server A, and she does not see those writes because they are not yet propagated, and it means that Alice does not see her writes. It means that read your writes is not satisfied. So in this video we have reviewed all session guarantees which we wanted to do. So first is monotonic reads, monotonic writes, read your writes, and the write follows read. For write follows read guarantee we also dissolved it into two parts, into two different guarantees, and looked at the difference between them, and then we compared those session guarantees with a consistent prefix guarantee. And as usual, I have this slide with a list of topics which are closely related to the ones which were discussed, but they were not included in this video. I'll do videos about them in future, so not to lose them, just subscribe to the channel and you will get notification when new video is ready and in production. Here is the list of literature which I used for investigation, research, and for preparation of this lecture. And that's it. You've been watching a video about client-centric consistency models. I'm Ivan Fedyanin. I'm a PhD and software architect. You can find more info about me on my website, fedyanin.ai, or at my LinkedIn, which is provided here. So, hope to see you again and wait for the new videos. Bye!